In August 2013, the Syrian government released rockets containing sarin gas into Ghouta, Syria during a civil war. At least 281 people were killed, while estimates claim that more than 1,000 lives were lost. The deadly attack shocked and horrified people around the world. This attack motivated us to understand how sarin affects the body. First, we're going to talk about the sarin molecule and its synthesis. Sarin, also known as 2-fluoromethylphosphoryl oxypropane, is an organophosphoric nerve agent with a high toxicity in humans. The compound was first discovered in 1938 by German scientists searching for a possible insecticide and was later developed into a chemical weapon during World War II. At room temperature, sarin exists as a clear, odorless, colorless liquid. It has a boiling point of 147 degrees Celsius, but is highly volatile and can easily be weaponized as a gas. Thus, the most common route towards exposure is inhalation. Synthesis of sarin is achieved by alcoholysis with isopropyl alcohol. The most common synthetic pathway is a reaction of isopropyl alcohol with methylphosphonyl difluoride, seen on the right. Sarin has a single chiral center at the phosphorus atom, and this synthesis produces a racemic mixture. While the S enantiomer is about 10 times more toxic due to a greater binding affinity for acetylcholinesterase, the racemic mixture is generally used when sarin is deployed. The synthesis of excess acid alongside sarin causes sarin to degrade rapidly, so additives such as tributylamine are often used to neutralize the acid.
Now we are going to discuss the biochemical function of sarin on enzymes. Sarin acts by inhibiting acetylcholinesterase irreversibly. Acetylcholinesterase normally functions by breaking down acetylcholine into acetic acid and choline. Acetylcholine is hydrolyzed by the serine hydroxyl group in the catalytic triad of acetylcholinesterase. Sarin inhibits acetylcholinesterase through phosphorylation. Sarin phosphorylates the serine hydroxyl group in the catalytic triad. Sarin is considered an irreversible inhibitor due to the process of aging. In the process of aging, phosphorylated acetylcholinesterase loses an alkyl group and forms a stable complex. This stabilized complex cannot be dephosphorylated, and thus the enzyme cannot be regenerated. In the human body, sarin exposure predominantly impacts the cholinergic system. The cholinergic system is responsible for higher order processing. Sarin inhibition of acetylcholinesterase results in the accumulation of acetylcholine at both muscarinic and nicotinic receptors in the central and peripheral nervous systems. Accumulation of acetylcholine at muscarinic receptors can result in the physiological symptoms of blurred vision, headaches, dyspnea, salivation, or diarrhea. Accumulation of acetylcholine at nicotinic receptors can result in the physiological symptoms of muscular twitching or weakness. Sarin can also lead to death. Disruption of cholinergic receptors in the central nervous system can result in the physiological symptoms of bronchoconstriction, central apnea, seizures, and respiratory muscle paralysis. Similarly, the disruption of cholinergic receptors in the peripheral nervous system can result in physiological symptoms of bronchoconstriction or diarrhea.
Now we're going to discuss the potential treatment options for sarin poisoning, one of which is known as 2-PAM. 2-PAM, also known as 2-pyridine aldoxamine methylchloride, which is composed of a 1-methylpyridinium component and an oxamine component. The pyridinium component binds to the anionic site of the acetylcholinesterase and ensures that the oxamine component is located close enough to the phosphorus of the organophosphate to create a bond with it. The oxamine group in 2-PAM has a very high affinity for the phosphorus atom of the organophosphate and has the ability to cause the bond between the organophosphate and the serine residue to hydrolyze. This releases the free serine residue and regenerates the function of the acetylcholinesterase. This only works if the bond between the serine and the organophosphate has not aged. Because of the positive charge on the pyridinium component of 2-PAM, the compound is unable to pass through the blood-brain barrier. A reduced variant of 2-PAM, known as pro-2-PAM, easily crosses the blood-brain barrier. Once across, it is oxidized to form 2-PAM and is able to regenerate acetylcholine esterase function within the central nervous system. While the harms of acetylcholine esterase inhibition are evident, recent research into its therapeutic applications are revealing promising disease interventions. Application of acetylcholine esterase inhibitors to patients suffering from Parkinson's disease has been shown to reduce cognitive and psychotic symptoms while not worsening the muscle symptoms that they have. We do not have a sufficient understanding of why this works, but in the process of understanding it, hopefully we will learn more about the treatment of similar diseases.